So like the previous problem, this is an energy conservation problem. Something's going to happen to the energy as this falling rock goes through these different positions. Okay, this is a rock. It's starting out at this position. And it's going to fall to this position, and it's going to fall to this position. And we're going to investigate what happens to the energy as the ball does that. Sorry, the rock. Well, the difference here is we know we want this potential energy, but or rather, in the previous problem we were given the potential energy. Now we're not given the potential energy. Does anybody have ideas about what we could do even though we were not given that potential energy? Okay, we're going to use the equation. So the potential energy in the beginning it's mgh. So a quick calculation, we just put in the mass of 3 kilograms. I deliberately just put this number in here, this 3 kilograms. I just threw that in there. Hopefully you would know what to do with that and you recognize that as a mass. And then G is always 10 on Earth. And then the height is 20 meters. So this thing starts out from a height of 20 meters. You simply do 3 times 10 times 20. That's 30 times 20. So 600 joules. Okay, it's good for the test. Remember those units. That's the units are joules. So we have 600 joules of potential energy. Does anyone have a guess on kinetic energy? 0 because that object is not moving. That's correct. When you drop an object, you can assume that it's not moving in the beginning. Does anybody want to tell me what the mechanical energy is?
600 joules.
600 joules. We simply added those up. Once I know the total mechanical energy, this is where it becomes kind of like a logic problem. Nick, can you tell me what else I can do with that 600 joules? Anybody want to jump in? Once I know mechanical energy is 600 joules, what can I do?
You put it in for
all of the
mechanical.
Very good. You can put it in for all of the mechanical energies because the energy doesn't disappear. 600 joules here. And down here, 600 joules. We're assuming no air resistance. In real life, of course, you lose energy because of air resistance. So the trick is, what do I do about halfway down? It's halfway down. So it's going to have half the potential energy. So the potential energy here is 300 joules. So the kinetic energy must be 300 joules. What about at the bottom? Even though, so I'm going to say, even though it may look to you like it's hitting the ground, there's a subtle thing happening here at the bottom. This is a subtle thing that has to be explained, and on the video you should hear this and think about this. But when we say at the bottom, we don't mean that literally. Because if we literally meant at the bottom, that's where the object hits the ground and loses all its energy. Loses its energy. Its energy goes to sound, heat, vibrations, and stuff. So what we really mean is just before, like a millimeter before it hits the ground. Okay, so the potential energy right before it hits the ground is 0, and the kinetic energy is 600 joules. It's almost all of its energy. Okay, if you say it's not perfect, okay, it's like 599.999 joules would be kinetic energy. So what you see is a gradual energy transformation from here to here to here that goes from potential to kinetic when something's dropped. You could go the other way. If you threw the ball up, This could easily be a problem about a ball being thrown up, and the same thing would be true. In the beginning, it would have all kinetic, then that would have less kinetic, and then would have all potential at the peak. Okay, this can go in two directions.